I welcome you again for this lecture on NPTEL course for earthquake resistant design of foundations. And as you are aware that we are right now in the third module of this lecture, which is on pile foundations. So, continue with that, as the pile foundation is very important for earthquake resistant design of foundations or for seismic analysis. During the pile foundations under this module, we already covered piles for static vertical load, lateral load on piles, dynamic analysis of piles, and then later in the last two lectures rather last 4 lectures we was discussed dynamic analysis of piles. And during those lectures we also discussed design for lateral and dynamic loads. So, that means the fourth one is already covered under the third one, and the fourth is now exclusively today we are going to talk on seismic response of piles. So, the difference, as you may be aware, that when we talk about dynamic analysis, the dynamic analysis may be due to any load including earthquake, but today we are going to talk for the earthquake load, that how to deal with the earthquake loads when the due to the seismic loads. So, we are going to talk about first what is called dynamic impedance, then we are going to talk about natural frequencies, and then seismic response also. So, let us talk seismic response of piles, and for this chapter, that is so called chapter 4, will be covered under these topics. We are going to talk introduction for the seismic response, what is the basic concepts, then we are going to discuss initial first theory on the pile dynamics for the continuum Seismic theory in 1969, and later Novak's 3D model, Nogami and Novak 1976, and another publication in 1977 with Novak and Nogami we are going to discuss. Then Novak is considered to be the kind of a father in the world for the pile dynamics. So, we are going to talk his paper Novak 1974, that is on dynamic stiffness and damping of piles, that means pile group is also considered in that. Then we are going to talk a simple closed form solutions for seismic response of end bearing single piles, which was published in Gazetas in 1984. So, let us talk about first introduction and then basic concept, and after that we are going to talk these 4 different theories in the 2 lectures. Out of these topics, the first 4 introduction, basic concept, Seismic theory, Novak's 3D model, that has been published in a journal paper, in a review paper, and that review paper is Maheshwari and Watanabe in 2009. So, all the details which we are going to talk is already published, it is not a new material, but this will be very useful for that, and it is coming from our own publication. So, and the reference you will find that detail in the reference. So, as discussed in the paper, proper design of pile supported structures require an adequate dynamic analysis of the pile foundations. So, that is well known to us, and recognize the importance of the soil pile interaction. Researchers have conducted extensive studies for analysis of pile groups, and development in pile dynamics started about 4 decades ago. So, this was like now it is because it was 2009. So, almost 5 decades ago. Initially proposed approaches were for one dimensional linear analysis of single piles in the frequency domain. So, the first few papers was in frequency domain, and later on it was extended for time domain also. And due to extensive research and advancement in computation facility, more sophisticated approaches have evolved over the time. Recently, researchers have proposed 3-dimensional nonlinear dynamic analysis in the time domain for pile groups. So, you may be aware that now, because one can do even the nonlinear analysis for 3D case and using finite element method. However, yet the relevance of the simplified theories developed in 60s and 70s is not diminished, and in fact, most of the later theories were just extensions of the few basic theories developed earlier. So, basic theories was developed in 60s and 70s, and later on that the research development took place. So, we are going to talk about the basic concept and that basic theories rather than finite element the 3D finite element methods or so in these 2 lectures. So, let us continue with this. How for the piles work started. For static loads on pile foundations, you may be aware that some of you might be aware that work was done by initially by Polas in 1968, the first publication, and the pioneer work has been done. However, that work for Polas was exclusively for static loads, it was not dynamic loads was not considered at the time. And for the pile dynamics, first widely known work is due to the Pengin et al. 1964, where they have done some consider the long piles for the under the bridges. And the broad sense research was primarily focused on linear dynamic analysis on this paper, Pengin et al. And substantial research efforts have been made on the linear run of single pile and pile groups in the frequency domain. All this work was in frequency domain. Further, the frequency domain work include Tazmi 1969, Novak 1974, Belne et al., Nogami and Novak 1976, Novak and Nogami later 77, then Kenya and Kozol, Gazetas, Dobry and Gazetas, Makris and Gazetas, El Nagar and Novak, and the recent one in for frequency domain in 2006 and 2009 by Maheshwari and Watanabe. So, these are the I know that this list is exhaustive, this is not a complete list, and this is like few of the papers which are published and which has been widely referred has been, these all are on time frequency domain analysis. Later the few researchers performed the time domain analysis, and the first work on for piles on time domain analysis for particularly for the nonlinear case come by Matlock et al. In 1978. Who developed a unit load transfer curve, that is PY curve, for the time domain nonlinear analysis. And based on plane strain medium assumption in the frequency domain, which the assumption was of Novak et al. Of 78, Nogami and Konogai in 1986 and 1988 have developed time domain analysis method for axial and lateral response of single piles respectively. So, there are two publications, one is for axial response, another is for lateral response of 1988, and these are for single piles. And their analysis use concept of what is called Winkler soil model. Later the time domain analysis using finite element concept is carried out by many researchers. For this one can refer the work done by this the time domain publication of 2004 and 2005 of Maheshwari et al. Can be referred for time domain analysis, including the nullity of the soil. So, in general it can be said that lot of work has been done for piles in frequency domain and time domain, and because this is this lecture NPTEL lecture is mostly for BTech or MTech students, and those who are like exclusively working on this topic on pile foundations for PhD work, then they can start their work from using the references today we are going to talk. But this will be a preliminary work, or you can say that simplified theories only. We are not going to talk very rigorous theories, and you will see that even the simplified theories have very complicated equations. So, little bit we are going to talk, and I will try to explain you the equations which are coming. But before that, let us discuss the basic concept. What is the basic concept? Here the concept is that during the vibrations the pile is going to interact with the surrounding soil. So, pile is not alone, that is the basic difference between a column and pile. When we talk about column, column is a simple structure, we do not talk about soil. But when talking about pile foundation, we need to consider the surrounding soil also, and as a result this surrounding soil will modify the stiffness of the pile and generating damping. So, what we are going to talk is ultimately the stiffness or damping properties of the whole soil pile system. It is not that only we are going to consider only pile or only soil. So, it will be together. So, and when we talk about a group, pile group, and for a soil pile group system, two kind of interaction effects are important. First interaction between soil and pile called soil pile interaction. If you have a single pile and you have a soil, then you can have interaction between soil and pile, that is called soil pile interaction. So, this soil pile interaction will be basically this will be applicable for single pile. So, I can say like this is for single pile. Then second is interaction during piles through soil, that is pile soil pile interaction. So, this will be applicable when we say pile group. So, you have a more than one pile, then it is typically called pile soil pile interaction in the literature. An adequate analysis of a pile group should account for both of these interactions, and this has been also interactions effect has been, you may be aware that Wolf 1985 very famous books on soil ester interaction. So, when we talk about soil pile interaction, so we need to consider the first one thing what is called SSI, and I am going to talk about SSI in the last module of this course, which is soil structure interaction. So, it is called soil structure interaction, SSI. So, when we talk about soil pile interaction or pile soil pile interaction, they are basically other forms of SSI only, where when you talk about soil pile interaction, you can treat pile as a structure and soil is a structure is replaced by pile. When you have pile soil pile interaction, that is basically between two piles you have the soil, so the group effect comes in picture. And when we talk about SSI, or let us say soil pile interaction, which is sometimes in short called SPI. So, for single pile you can say SPI, and for pile group you can have PSPI. So, this way you can have different terms, but as for the soil structure interaction SSI itself is concerned, there are some basic issues, though we will talk about those issues in very much detail when we talk about SSI. But very common problem is that soil is a semi infinite medium, it is not finite medium, and a major problem in dynamic soil ester interaction is modeling of the unbounded soil domain. So, first issue is modeling of soil domain, and for dynamic loading structures, whether you say piles or superstructure, they always interact with surrounding soil, and it is not adequate to analyze the structure independently. So, the issue is here the modeling of unbounded soil domain, this is a major issue, and about this issue we will talk in detail. But in general the issue is when seismic loading is applied to the soil region around the structure, then this region should be modeled along with the structure in such a way as to satisfy the radiation condition, and the radiation conditions, that is only waves can radiate outside the considered region and they cannot come inside this boundary, and thus this boundary represent an energy sink where only outgoing waves exist, and it is and then finally we need to enforce the compatibility in a force equilibrium condition between soil and pile along the pile surface for each pile considered. So, modeling of unbounded soil domain, there are plenty of literature available on modeling of unbounded domain, even there are books on the unbounded domain itself that can be referred, but right now like this, if we can, one can refer this publication by the book by Wolf 1985. So, this will cover all these details, and further detail we will talk about when we talk about SSI. So, then this was some basic concept. After this some basic concept that means for any interaction effect, first thing is how you model soil, the boundary, how the unbounded soil domain is modeled. So, first work as I mentioned that in 1968 Polas have considered the settlement of pile groups, and when this work, and this has been already discussed, that this work was for static analysis. So, it was not for seismic or dynamic analysis, but the work started, and they have considered both a single pile as well as pile group, and not only single pile group is considered, both axial and lateral modes of vibration were considered. That means, vertical mode of vibration is considered as well as horizontal mode of vibration is considered, and the theory is able to deal with end bearing as well as floating piles. So, that means it is very versatile. So, you have this single pile group, you have end bearing pile, floating piles, both mode vibration is considered. So, however, the soil is assumed to be an ideal elastic homogeneous isotropic mass having constant elastic parameters. That means, nonlinearity of the soil is not considered, inhomogeneity is not considered, and isotropy is not considered. Though this idealization differs in many respects from reality, but it still gives satisfactory results. And when we talk about pile dynamics, the Polas theory may have little significance for because they have considered the static load, not dynamic loads. So, as a result, the frequency of loading or natural frequency or the dynamic response does not come in picture. However, this theory provides a base for the development of various dynamic theories. For static case, Polas defined few key factors like interaction factor for pile groups. So, this term was used later for dynamic analysis also. which were subsequently defined for dynamic analysis in the same fashion. So, the polars kind of you can say that set trained of using static analysis, then the same theory has been you can say kind of extended for the dynamic analysis. Also for parametric studies, slenderness ratio, spacing between piles, relative rigidity between soil and pile were used by polars, which were later used in the dynamic theories in a similar fashion. So, one thing is interaction factor, other thing is the parametric study. So, polars have considered when analyzing the pile groups, that what is the spacing between piles, what is the relative rigidity between soil and pile. So, all these issues have been later considered, those who have carried out the dynamic analysis. Then the Pengin in 1964, though the work is from before the polars, but here they have considered the discrete models. So, Pengin et al. In 1964 presented a nonlinear discrete dynamic model for piles passing through deep clay medium. So, even the nonlinearity is also considered, and this was appeared to be the first work on the for the dynamic analysis of piles. And these long piles were used to support a highway bridge. Horizontal mode of vibration is considered in the study, and this model being a discrete model, that means a combination of using spring and dashboard. This allows for nonlinearity and account for gapping between soil and pile. So, material nonlinearity of the soil is considered, as well as the separation between soil pile is considered. So, that this is at that time naturally this was quite advanced, and however, it is very difficult to incorporate radiation damping and inertial effect of soil is accounted only approximately using lump masses. So, what is the drawback? That because it is based on discrete models. So, first thing is the inertial effect has been cannot be properly accounted, as well as the radiation conditions or radiation damping has been not properly considered. Since radiation damping of soil are important parameters in SSI, hence this model is not rational for dynamic analysis of pile groups. So, this was like a kind of approximate method only for the analysis of pile group. Now, we are going to talk about what are the for dynamic analysis for structure embedded in elastic system Seismic 1969. So, perhaps the Seismic was the first one theory which has been proposed for dynamic analysis, and in this case based on the continuum. So, that means though this theory is for elastic, not nonlinearity is not considered in this case. However, the inertial effect as well as radiation damping is properly considered in this case. Moreover, Seismic's theory was for horizontal vibration only. So, what has been done here? Use a linear viscoelastic stratum of the Kelvin-Vogel type to model the soil and did not consider the vertical response. So, that means first of all, though it is for dynamic analysis, they have considered in the lateral direction, not in the vertical direction. So, in horizontal mode of vibration, this model is used only for dynamic of single pile resting on ridged bedrock. So, viscous damping of the soil stratum is taken into account. For the analysis of single pile, this theory was extensively used in Japan and described in detail as Seismic's theory in later slides. So, detail of this theory we will talk later. So, right now this is this is for horizontal mode of vibration, it is for end bearing piles. So, these things are like and that elastic medium has been considered. Then Seismic 1969, later this continued with the work of Novak, and then in Nogami and Novak in 1976. The first one is for vertical vibration and the second one is for horizontal vibration. So, two publications, one by Nogami is the first author, and in the second publication as Novak is the first author. So, these two publications, the first one is for vertical vibration and the second one is for the horizontal vibration. So, Nogami and Novak in 1976 developed a rigorous method for dynamic analysis of a single end bearing pile for axial vibration. So, Seismic also considered the single end bearing pile, and these researchers Nogami and Novak also consider the single end bearing pile, not the pile group, and only the end bearing pile has been considered. So, for the one have considered for axial vibration, which was not considered by the Seismic, and Novak and Nogami extended the same for horizontal vibration. This theory is based on 3-dimensional model and fully accounts for soil pile interaction. So, this was the issue, like another theories, like suppose in Pengin's et al. In 1964. So, it is difficult to account for soil pile interaction because only discrete model has been considered. Soil reaction is completely derived in this theory from basic principles. Hysteretic damping of soil is taken into account. This is most advanced theory for a single pile for linear elastic analysis in the frequency domain and described in detail as Novak's 3D model. So, later on this theory which we are going to discuss in next slides will be treated as a Novak's 3D model. So, this is most advanced theory for a single pile for linear analysis. Okay, so after this introduction, then next one is for modeling for end bearing single pile system. There was between plane strain soil model which I will skip it. Modeling for end bearing single soil pile system, it is given here. So, let us say that first of all for a single pile and particularly when the pile is end bearing pile. This is the simplest case for considered to be for dynamic analysis of the piles or let us say seismic analysis of the piles. Here what is done here that the two cases A and B are given. A is the case when the single vertical pile which is resting on a bedrock is subjected to vertical load and which is P E I omega t. So, this is for vertical vibration and this is for horizontal vibration. In the first case, when you apply the load from the top, what will happen? This load will try to push the pile down. So, as a result the displacement will occur in the vertical direction in downward direction which is shown as in this. So, displacement is shown by this W z E I omega t and it is saying what is z? Z is basically depth, z is not shown here. So, this is z is this. So, what you can see here that as you apply the load, the displacement in the vertical direction varies with the depth as well as time with the time because your load is also varying with time. And this load is registered by what is called the soil reaction which is acting in upward direction which is shown in here P z E I omega t. This was the case when dealing with the vertical vibration. So, this is basically I can put like this is for vertical vibration and this is for horizontal vibration this. So, for horizontal vibration which is more important in case of earthquake, when you apply the load horizontally what will happen? The displacement will also take place in the same direction in the load and the displacements are shown using what is called U z E I omega t. Okay. And the soil reaction which will try to resist the load applied load is given by P z E I omega t as shown here. H is the thickness of the soil layer or thickness of soil stratum, while 2 r 0 in these both figures are r naught is the radius of the pile. What is r naught? Which is understood also radius of pile. Okay. So, these are the modeling done and this modeling has been done. Let us say what we are discussing is Seismic theory. Then in continue with Seismic theory like this modeling is general which will be for Seismic as well as for this latter one. So, let us talk about the Seismic theory was for horizontal vibration for this case only B case. Seismic theory was not for the vertical vibration for the first case. So, for the second case where the for horizontal vibration where the Seismic theory is applicable. In general this theory is applicable for dynamic analysis of a structure embedded in an elastic stratum and vertically supported on the underlying bedrock. So, this we already discussed about that. The analysis involved application of 3-dimensional wave propagation to the stratum overlying the bedrock. So, based on 3D that means it is not a plane strain condition or something like this. What are the assumptions? The modal ground consists of an elastic stratum resting on the bedrock. So, this is the case here you have a ground which is resting on the bedrock and it is assumed that property is elastic. A pile or pier of cylindrical shape resting on the bedrock is fully or partially embedded into the stratum. So, here it is assumed by Seismic the shape of the pile is cylindrical. that means its cross section is circular. The vertical displacement of the surface layer is neglected because it will be less significant than the horizontal component, that is okay, because you are applying your load in the dynamic load only in the horizontal direction, not in the vertical direction for Seismic theory. So, it is expected that displacement will be more in the horizontal direction, not in the vertical direction. The viscous damping of the stratum is considered for the shear velocity travelling along the depth. The input acceleration is applied on the surface of the bedrock. So, these are the assumptions of the Seismic theory, and continue with these assumptions. After these assumptions, let us discuss. So, what you have here, formulation and solutions. Since vertical displacement is neglected, hence analysis requires solution of two wave equation in cylindrical coordinates, and cylindrical coordinates when you consider will be r, theta and z, where z is already shown in this figure. Z for here also z will be like this, r will be along the when you draw the this plan. So, r and theta will be like so varying, and theta in cylindrical coordinates they will be varying. So, you have r, theta and z. To separate the variables, two potential functions are involved, which reduces the original equation of motion in the form of modified Bessel equation. So, what is done? Using the wave propagation concept, write the equation of motion. Once equation of motion is ready, then you solve the equation of motion, and first you write in the modified Bessel function equations. So, I am not going to go in the derivation, but we are going to talk about solutions. By eliminating unknown constant with respect to boundary conditions and expressing resistance of soil in terms of displacements, it will lead to what is called complex soil stiffness of viscoelastic soil medium for horizontal vibration. So, this is important. So, ultimately our end product will be complex soil stiffness. Why we are saying complex here? Because there will be real part as well as imaginary part of that stiffness, and that stiffness is applicable for viscoelastic soil medium. This will be frequency dependent dynamic stiffness of soil and employs what is called modified Bessel functions. Once soil resistance at a particular frequency is known, solation of the pile soil system is performed as a beam, and by enforcing displacement compatibility and force equilibrium between soil and pile, the unknown constants are found. All formulation is in continuous form, and final solution is as follows. So, let us discuss the solution given by Seismic. What Seismic did? Let me again summarize. Seismic's theory is only for single pile, and it is a single end bearing pile, and it is considering horizontal mode of vibration only, not vertical mode of vibration. So, for the horizontal mode of vibration, when you apply a load horizontally, then the soil reaction Pz, which is varying along with the depth, is a function of displacement, and that means it is related to displacement. How the displacement varies? According to you can get the soil reaction. So, Pz is given using equation number 1a, where mu first, and this is a basically shear modulus and Lem's constant, un is displacement, amplitude of horizontal displacement, z depth, and h is the maximum value of z. Okay. So, now the one most important point is alpha Hn, where it is a dimensional resistance factor. So, alpha Hn does not have any dimensions for NTH mode at a particular frequency omega, and is given by alpha Hn is given by from this relation here. So, if you see here alpha Hn is given from this relation. In this relation omega, this is capital omega n is given equation 1c, and in the equation 1c in denominator high n is coming. So, which is given from these relations, and in these relations both 1c and 1d you could see there are qn and another quantity Sn is coming. R naught is already defined. So, now we are going to talk what is Qn and Sn, and first of all K0 and K1 are coming. So, K0 and K1 are modified Bessel functions of order 0 and 1. So, K0 is for so this is defined later also. What is Qn and Sn? Qn and Sn are the parameters related to frequency, which is defined here. Qn is omega n Wz Vl, and this is Vs. So, omega n is basically damping measure. So, damping here n, first of all n in these equations, basically n, what is n is the nth mode which we have already defined. So, when n equal to 1, you will get for the all the things for first mode. So, what you have here for the damping ratio for the nth mode is defined from this relation when n is the number mode and omega is frequency of excitation, the omega g is lowest natural circular frequency of the surface layer and given by this relation, where Vs is given from this relation, Vl is given from this relation. So, once Vs and Vl is known, you can calculate the value of omega g. Once omega is known, you can find the value of Qn and Sn, where the damping ratio sigma sigma n is xi n is given by this relation 1e. Okay. So, using these relations, ultimately we end up and you can get the value of alpha h n, and finally this p z equal to this, where summation is going from n to infinity 1 2 3 and infinity. So, we complete this, and this was complex solution. Actually what happens, if you have equation number 1a, in equation number 1a you will get two parts, one is real part, another is imaginary part. So, the real part, and because both real and imaginary parts are there, so it will be called what is called the complex soil stiffness. This was only considering the soil, there is no pile. Actually we consider the dimension of the pile here in this analysis when we talk about complex soil stiffness, but the property of the piles are missing in all these equations. We have not considered any property of the pile so far, only the dimension of the pile is considered there, which is r naught radius of the pile. The material property is not considered, and extending the same complex soil stiffness, the Tasmi extended for pile head stiffness. That means, pile head stiffness is simply, you can define, suppose this is pile and I apply a load in the horizontal direction at here at the top pile head, and at the same point at the pile head, if I find the displacement. So, complex stiffness will be simply the force which you are applying divided by the displacement. So, force divided by the displacement will give the stiffness. So, the complex pile head stiffness, which is defined in this manner, this is given in using equation 2a. This can be defined as the force at the head of the pile due to unit displacement can be written in complex form, where real part represent in spring constant while imaginary part represent the damping, and this is expressed in equation 2a. In the equation 2a, what is EI? EI is flexural rigidity of the pile, not the soil. H is the total thickness of the soil layer or the length of the pile, being the end bearing point, which will be the same. Then only the thing in this equation is what is this function fz omega. This function fz omega is a dimensionless function, and this is called dimensionless flexibility function f, and this is given by these relations. So, you have fz omega. So, you could see that this is given by these relations, and then you have the value of alpha 2 is given by this relation 2c. So, in alpha 2 what you see is EI is the flexural rigidity of the pile, while mu is shear modulus of the soil. So, alpha 2 will include property of the pile as well as soil. Then once alpha 2 is known, then substitute in this equation, and then you can work out summation, doing summation, ultimately you end up in the flexural rigidity, which is a function of z. That means, it will be different at different depth z and omega, this is frequency of excitation. Z is directly coming as in this equation. So, accordingly this function will vary, and omega is coming in this first part. When you change the value of omega, then naturally the value of fz omega is going to change. And as mentioned already, E, I, rho p are the Young's modulus, moment of inertia, mass density of pile respectively. So, this way we can have. So, and then Novak's 3D model, Nogami and Novak, which was also similar to what we have discussed for Tasmi's theory. So, we will discuss this in the next lecture. With this I thank you very much for your kind attention, and we will continue in the next lecture.